Thank you. It's an honor to be invited to give this talk. I may say a few words about my understanding of Hamburg University. My teacher, Chern, graduated from here with his PhD under Bratsky. So I always know somewhat about Hamburg. Except only a few years ago, I learned from the first paper, Kähler, on Kähler geometry. I found out something rather remarkable. Namely, first of all, he defined first Chern class by Richie Kircher already. And also, he wrote down the complex Monod-Ampere equation for Kähler symmetric in the very first paper in 1932. So basically, he asked the question how to construct a metric using complex Monod-Ampere equation. So a special form of the Calabi-Yau conjecture. So I was rather surprised to know that it was born here in Hamburg University. Anyway, so today I'm going to talk about some work that I did with my postdocs in the last many years, and especially on more algebraic stuff, which I think is fascinating, on holomorphic partial differential equations. So there are two parts. One part I'm going to talk about periods. The second part with about conical singularities relate to superconformal field theory. The first part is period integral. This John worked with many people in the last 10, 15 years, majorly with Bongliang. And so these are special functions that we like to understand how to relate to complex geometry. So why we are interested in this is because the first major calculation on Miller symmetry, which has been so fundamental for string, was due to Candelas, where he has to calculate periods of integrals for the quintic. So the period he was looking at is in this formula, where you have the integral written there in CP4, and you take the residue on the three-dimensional quintic, and this becomes a very important quintic over the many years. The quintic is defined by this function f. This function f will come up again and again in different forms in the later PowerPoints. So hope you remember that. It's a pencil. It's a session which defines a family of Calabi-Yau as a hypersurface in a Fano manifolds or Toric manifolds. Okay, so there's a great deal of effort to do this calculation. We would like to understand what happens to them, and this was generalized to more than one parameters by several group of people right after Candelas' work. So it has been very important. This is complicated because the number of parameters is getting bigger and bigger, and we have to understand it in more theoretical terms. Although calculation, numerical calculation is possible for low number of parameters, but in general, we got to understand it in a more fundamental and theoretical way. The reason we need to understand it is there are many problems in Miller's geometry still depend on understanding this integral, because we need to understand analytic continuation of the Miller map and also the instanton partition function, and all these are still a mystery when it's away from the large radius limit. So that's why one of the reasons I spend works with all my co-authors, my postdocs together to try to get better understanding what these periods are. Well, periods, of course, are studied long time ago, so I'm going to take a brief history. This is the Euler-Gauss hypergeometric function. From the name, you go back to Euler, or even slightly earlier than Euler. And then Gauss studied it, and Riemann and all these people study it. So this is the hypergeometric equation where we know there exists a power series solution of the form on the bottom, where we write it to be in this form. And this form will appear again later on, where we replace ABC by some divisors. And of course, there's a Legendre family of elliptic curves, which is well studied in number theory, and of course in algebraic geometry also. And we have this lambda, which is a parameter, where we have identified some canonical identification between h1 of y lambda with the standard C2, h1 of the tori. When lambda varies in a canonical contractible neighborhood around lambda naught. And there is, oh, that's good. And there's a one form which will be generalized to holomorphic n form later. And this holomorphic n form so we are interested in the integral omega lambda. It defines a cohomology class in H1 of TC. Oh yeah, okay. So omega lambda is the one form. In high dimensional, it will be holomorphic n form. And we try to understand the integral. Yeah, it defines a cohomology class on H1. So this vector changes holomorphically when lambda is changing. But it's moved in here. And this defines an important quantity that we are interested in. This is called period integrals. So given a base in homology now, we are interested in how they changes. These are canonical base because it depends only on topology. And we are interested in understanding fundamental periods. So these are called period integral. Omega lambda, the holomorphic one form here, integrate over the canonical base. So even though they are defined locally, the period integrals admit analytic continuation along any path in the moduli space B. Therefore, this period integral generates a local system on B. So, so this is an important quantity that we're interested in. And the period integrals are precisely the solution to the Euler-Gauss equation defined here, because you just check that by looking at the integral, and you find out that you satisfy the equation when you're operating L on the omega lambda. On the integral, before you integrate, you satisfy the equation already. So therefore, because it's exact, so therefore it's equal to 0. And so this is a general theme of how you solve the period integral. The integral satisfies some equation, and therefore you try to solve the equation and know the answer. So this is sometimes called the Picard-Fuchs equation, and this gives you a way to calculate the integral. Reduced to determine the two constants in the general solution to an ODE. So how do you find out the special solution? The constant you obtain by some special degeneration. For example, y lambda will degenerate to a null when lambda equals 0, and you see how they develop a pole when lambda equals 0. By looking at it carefully, then you can use that to determine these constants. So that's how you calculate the integral of the periods in that way. And so, for example, in this case, you calculate integral gamma 1, you find out this function, and gamma 2 is another base of the elliptic curve, you get this. And G1 lambda is a unit power series determined by the Euler-Gauss equation. So this tells you how to solve the problem finding the elliptic integrals by reducing it to the geometry of curves. So this whole thing, we will generalize it to a high dimension. So put in a more abstract manner, because we are going to write something in a more general way, we take a B to be connect complex manifold. So this is the parameter space that we are interested in doing. And this parameter space is a lambda that we had before. And then we take E be a vector bundle associated with flat connection. Sometimes it's called Gauss-Vanishing connection. So del is the connection. And so and we have a pairing between E and E star. E star is the dual of it. to OB. OB is a space of functions, holomorphic functions defined in B. We have a usual pairing between them. And given a fixed global session, S star. So E star would be the cohomology. And we define the period sheaf. So once you fix this S star, we define the period sheaf to be a sheaf of functions in the sheaf holomorphic function on B. It's the image of the map. You take kernel this connection, so that means a flat session, and then you define this. So this is just a little bit fancy way to say that you integrate. You look at the path in the flat connection, Gauss-Manin condition. You integrate. You look at the period over that path. But this will be notation we use from now on. Okay. So you fix S star, and then you define this period. Now, suppose we have a family of d-dimensional compact complex manifold over B. It's a family of parameters of B. And YB will be pi inverse B. So each YB will be a Calabi-Yau manifold itself, so parameterized by B. So from the cohomology, we form a vector bundle E star, which is just push forward of the cohomology group. And it is called E star. The dual bundle has fibers, which is homology group. So we have a natural pairing defined this way. So this is a Poincare pairing. E is equipped with a canonical flat connection that we mentioned earlier. Okay. So now fix a S star. So it's a cohomology class representing S star B. B is a point in the modular in the parameter space. S star B was simply an element in here, a cohomology class. So it's a closed form. We write it to be a closed form by the Ram cohomology. And we represent gamma, which is a element in a cycle in YB in the Calabi-Yau space. And then we put a pairing together. So gamma dot with S star B. So it's simply the integral of B over gamma. We call this FB. We shall use this notation from now on. F will be, we call it the universal period, universal session. Okay, this period integral Y with respect to S star. So when we fix S star, we have a well-defined FB. Okay, so it will be a function defined this way. So given a compact Kähler manifold S with D plus 1 dimension, we take the family over it so that it's a smooth Calabi-Yau hypersurface defined within this compact Kähler manifold. Okay, so it's for example, in the quintet, we have a family of quintet sitting in the CP4, and associate a flat bundle, as I mentioned earlier. Then this subspace form a subbundle sitting E star. Okay, so for each YB, which is a Calabi-Yau hypersurface, parameterized in this way, and we look at the holomorphic form, N form sitting there. These are of course defining a cohomology class. This defines a subbundle sitting in E star. Okay. Okay. It's just rewriting it in more fancy manner. But in this more abstract way, H top admits a canonical trivialization in terms of explicit family version of the Poincare residual map. So in the special case of the quintet, that was what I wrote down earlier. Omega is a holomorphic D plus 1 form. That's CP4, and then we take the residue of them. Okay, so this is F is the previous writing that I wrote down. F is the universal session defining the hypersurface family. So the Riemann-Hilbert problem for the period integral is to construct a complete system of partial differential equations, holomorphic partial differential equation, so to solve the period integral. So we like to study the explicit solutions and the monodrony of this local system. So that was the point of this part of the research. So we want to understand them. And we want complete means that the solution should be exactly the period integrals. So first of all, the period integral has to satisfy this system of equations, and vice versa, the solutions should give rise to those periods. So an example is a method provided by Duval and Griffiths, and you can do that, use to derive differential equation. Usually works for only one parameter family, and not quite for high parameter families. It's too complicated. And this can work out for this class of ODE, Gauss, the Euler-Gauss equation. Now, so let's discuss about toric manifold, which has been used extensively by people working in Miller symmetry. So let's take xd plus 1 be a toric manifold with respect to toric action. So it's important to have a toric action acting over there. And we assume the first train class of the total space is non-negative, for example, a Fano manifold. And we assume the generic Calabi-Yau hypersurface is smooth. So, for example, the first example was CP4, and we have a quintic sitting there. And this is more general than that we are talking. So we take a family of all such hypersurface. We take this family and call it pi, which is y over b, where b is a parameter. Now we take the Lie algebra of the tori cross C star. So we call it T hat. Okay? So T induces linear action on the holomorphic n forms on X. And also C star X by scaling. The n forms you can scale it. So in this case, we have a Lie algebra action acting on the endomorphism of they're acting on x0 or minus kx. This holomorphic sections of minus kx. So this gives rise to a family of operators, because each this Lie algebra has is a Lie algebra, and each y belongs to there, give rise to these operators. So these operators are going to play an important role for us. And we define a beta, which is a character on this Lie algebra, which takes value 0 on the tori, and takes 1 on the Euler operator. The Euler operator is the scaling operator coming from scaling. So this is important operator, beta. Now, each section of x0 and minus k restrict to tori has a Laurent polynomial. So it has a base of Laurent monomials, which is important base, x mu j, and in the x0, xd coordinate on t. So for toric variety, x is actually just a compactification of the tori, c star to the power d plus 1. So we have a Laurent expansion in terms of x0 up to xn. And the period integral of the family of Calabi-Yau hypersurface in X satisfy the following important PDE system, holomorphic differential equations. So it satisfies this box operator operating on the period equals 0. And the box operator is defined in the following way. It's equal to this, where the L's are integral vectors such that summation I, L, I, mu I comes from the Wick vector, and summation I, L, I equals 0. So this defines a large family of holomorphic differential operators, partial differential operators, etc. here. And then you have this other equation that comes from the action of the tori plus C star. So this system is called a GKC hypergeometric system, which was introduced by 3 people and led by Gelfand. So a theorem of GKC says that this solution is actually finite dimensional. And, but this system, unfortunately, is not complete. There are always more solutions than the period integrals. So given the period integral, we know that it's solved this system equation. But there are more equations than more solutions than this system. So we have to find a way to pick up the period solutions, period integrals out of the solutions. It's not complete. So we are interested in how to understand this, this period out of this system. So there are not too many examples that we can do, even in the case of a hypersurface in a flat variety was open. So we shall discuss about the progress in understand how to calculate these things. So it's better understood for toric, but not so much for general cases. So about 10 years ago, Bong Leung and I, and then later we have students and some postdocs working on this. So we introduced which we call tautological system. So the situation is this. So this is more general than toric manifolds now. So we take a projective manifold, and we have a complex algebraic group acting on this manifold. So we have a group action, and we take an equivalent base point free line bundle on X. So I take a line bundle which defines an embedding for me. So X has being a projective manifold, you have line bundle, but we want it to be equivalent under the group G. And we look at the space of sessions of this line bundle and take its dual, and we call it V. So V star would be the sessions itself. Now, given the embedding X into projective by V, this defines an equivalent map because we assume L is equivalent under the group action, and GX on X, and so this would be a nice equivalent map. And given this embedding, we have an ideal of the functions dividing image of phi X, because image of phi X is an algebraic variety by itself, so they're ideal of functions dividing it. So this L phi is important. And then, of course, we have a natural symplectic pairing between V and V star in a standard way. dV star is a ring of polynomial differential operators dividing on V star. So we have a ring of polynomial differential operators on V star. So these are the notation I hope you can remember. So first of all, there exists a line bundle L, which is kind of ample, defines an embedding for you into PV. And then associated to this embedding, we have an ideal of equations defining phi X, and this becomes an important ideal. And then we use dV star, it's a ring of polynomial differential operators on V star. Okay, so what do you do with this? Let's just give you some examples. So, which is a simple case, is P2, X is P2, and group G is PSL3 acting on X, and the line bundle is O3. So V star is now symmetric product of C3, so X naught of L. And this gives you a Sager embedding of X into projected by V. And so the embedding is explicit, is given by here. So this is a phi that I discussed before. L phi is the one that we discussed earlier, the quadratic ideal generated by the Veronese binomials coming by understanding this embedding on the Sager embedding. Okay? And dV star would be simply the Y algebra acting on V. So AI is the coordinate that we choose in V. So there's a Lie algebra mapping V star into the derivation of symmetric V, which is basically a Fourier transform. Zeta mapping V star is just differentiated in this way. The linear action induces a Lie algebra map, which is redefined by Cx. So this is similar to the previous GKC system where we have this Cx. Okay. Now, if I choose AI and zeta I be a dual base of V, AI will be based in V and zeta I will be dual, then differentiation with respect to zeta I is differentiation of AI. So that is the notation that we shall use. So what we call a tautological system is the following thing. It's a left ideal tau XLG beta. So X is the projective manifold like CPN. L is a line bundle like O3 that we just discussed. G is the PGL3 that we just discussed. And beta will be a constant, a complex number. So we look at all the possible polynomial operator that comes from L phi. remember what alpha is. Alpha is the ideal defining the embedding phi x under embedding. And Cx are the G operators. Remember, we have the T tau, which come from the Toric action plus C star before. Now we just use this G, the Lie algebra of G. And then we have this Euler operator, which we define to be summation AI d over dAI plus beta. This whole system of differential operator is a core tautological system. So it's a left ideal in dV star generator. So we proved in the case there's only finite number of G objects, this tautological system is actually regular holonomic. So finite dimension, the solution space, and the solution rank. This is a system of ODE, not ODE, holomorphic PDE, and the solution space is finite dimension. And the rank is bounded both by the degree of X sitting in PV in a rather general situation. And so one can prove several coordinate out of it. For example, power series must be analytic, formal power series. And the sheave of solution is locally constant sheave of finite rank. So the period integral, we proved that the period integral of the family is actually a solution to this system, this tautological system. So given any compact G manifold such that minus Kx, the entire canonical bundle is space-bound free, then we prove that it is finite dimensional. And it satisfies the tautological system. So this is useful to know. And now we also find out that the solution rank, so tau, which we call tautological system, has the finite dimensional solution. The rank of the solution actually at any point in our parameter space actually is just dimension of the complement of the Calabi-Yau manifold in the ambient space in the n-dimensional cohomology. So this solution rank can be calculated. This is geometric. You can calculate it by many other useful situations. The proof uses the method of Dinker to interpret the Dirac cohomology of the complement and the Lie algebra homology group of certain G module. So this is established, and these are useful. And then immediately afterwards, Wang, Liang, and Zhu Xinwen generalized it, remove some hypotheses. So he said that if we have projected homogeneous G space, then the solution rank of tau at any point sigma is exactly that, when it's homogeneous G space. And so this gives rise to an interesting thing. So the rank of the period integral that we are interested in calculating is less than equal to rank of tau. Tau is the tautological system that we know how to calculate, and this bounds the rank of the solution system. Now the question is equality. So when is it actually equal? So we want to say that they are equal. Then in the case of homogeneous space, the tautological system is complete. That means they're equal. It's equal, if and only if the primitive cohomology is equal to 0, as a consequence of this formula and the freedom due to Wang, Liang, and Zhu. So in the case of homogeneous space, that's good. We know exactly when is it true, then it's complete. So complete tells you that the solution system is exactly given by the tautological system. And so there are special cases which can be computed, and the system is complete in the case of projective space in particular. And some of this was conjectured by us many years ago, 20 years ago. Anyway, so this we call it geometric rank formula. And now there's an algebraic rank formula which we developed so that it can be computed by using algebra. Then this is developed about 4 years ago when Spencer Brock was visiting us in Tsinghua University. And the Sorotan rank of tau, this is the tautological system that I mentioned. At any point sigma is this dimension. So this is more algebraic. So the ring, the whole ring is there of anti-canonical ring. And in the case of Pn-1, you can write it down and very explicitly and in terms of all this space, so you can compute it. And these are useful. So this formula is interesting when the Sorotan rank of tau is exactly 1, because that is related to the large complex structure limit, which is interesting for linear geometry. So in that case, we know there should be 1 regular Sorotan. And so this does not imply it must be large complex structure limit, but it's a necessary condition. And so we can use this as a criteria to look into that. For example, in the Grassmannian 2 planes sitting in n space, we have some candidates that we know how to do. And there it can be generalized to more general G mod P, and based on some classical multiplicity freedom in Weimar modules. Now, more recently, Shing-Tung Yau, who is a student of mine, we look at the mod P solution to the tautological system. It gives a very strong constraints on the mod P behavior of this holomorphic period, and it can provide complete information about the period, actually, it turns out. So these are interesting that mod P comes in. So we have the geometric rank and also the algebraic rank formula, which are useful. And then it turns out there are some interesting questions called chain integral, which we would like to say a few words about. So if you denote x minus vb, so the complement of the Calabi-Yau, and you take union D to be union of all G invariant devices in X, and you take any relative cycle here. That's why it's called chain. It's a relative cycle. The chain integral turns out to be an analytic solution to the tautological system at B. So this integral is interesting. It was studied actually by some physicists before, and so from this we get from this chain we get a map to the space of local holomorphic solutions of tau at B. So this gives rise to an interesting class of objects that we are interested in. Turns out we can prove that if X is a smooth toric variety and take G to be the toroid acting on X with the open dense orbit, then the chain integral map is actually isomorphism. So this is good because that gives rise to all the solutions. So these are based on some rather interesting calculation. In this case, it reduced to GKC system because we are talking about toric variety now. And this was studied by several other people before. They call it semi-Pérez. We call it a little bit differently. Now, in the case of G mod B is a complete flat variety, we take the group to be a Borel subgroup B, then the chain integral map is an isomorphism. So remember, the tautological system depends on which group you choose. So in general, it may not be surjective if we associate with different groups. There could be because there could be lower dimensional chain invariants under the group action that can contribute to the solution of tau. But in any case, we can generalize it to a more general situation. Now, there's an important hyperplane conjecture related to what Candelas and other people did. So this was studied by Hosono and Bongliang and myself many years ago. So in the Toric hypersurface, there was a construction due to Betreff, and you take reflexive pair of dual polytopes in Rn, and you construct a fence over them, and then you construct Miller family, Miller pairs associated to del, sigma, and then the other one. And this, if you take a Krypton resolution of X, you give a Krypton resolution of the Calabi-Yau hypersurface. And this defines a interesting situation. So first of all, it admits regular projective translation triangulations. So this gives rise a corresponding projective resolution for X and X hat, the Miller. And then you will look at the Krypton resolution, and you resolve it, you get H2 of it. This gives T invariant, torus invariant divisors in X. And you define summation of these di's as a divisor and correct D0 minus of it. And the Calabi-Yau manifold would be summation of Pi as a divisor. And then look at the set of integral points in the Morley cone of X tilde. Then you can write down the following theorem due to several people. And the rank of the solution of the tau GKC, the GKC system, is actually can be calculated by the volume of delta. So this is known in the 1990s. Now, on the other hand, we actually want to solve it, and we conjecture the following statement. We take the large radius limit where A0 is large, and you take Bx on the in the neighborhood large radius limit, and we define it in the following way. This map, we call it B series. So this generalized the concept of the hypergeometric series expansion, except we replaced those numbers by the divisors in this way. So this form an interesting formal power series that comes up. And this B, we proved that long time ago, the solution space of the periods is a solution of this certified the GKC system related to this. The period integral we conjecture to be precise, to be exactly generated by the functional component or the cup products of this Bx that I just defined by couple product with Y tilde. So, so this is the conjecture we make, and this was proved in only in some special cases so far. And the general case is still unknown. So in particular, it's proved by Bongliang and Zhu 2 years ago in the case of P4. So where in that case, B is actually just the well-known formula written by Candelas and his friends. And so this reproduced the formula of Candelas. But the point is that you want to prove that, yes, exactly, from the GKC system, you can reproduce exactly. Now, already in the case of the X taking to the middle of the quintet is already a big family, so it's not easy to prove. So the difficulties come up from the fact that there are many different Krypton resolutions of X, and it involves rather complicated combinatorial choices. And most of these Krypton resolutions are not Fano manifolds. That's this cost problem. And so there are some ideas which I was written in this transparency, but I don't think I have time to go through that. So let me not go into description of how to prove it here. So, so the second application of the Riemann-Hilbert problem that we are talking about is to understand monodromy invariant differential zero loci. So we need to understand the monodromy also, besides solving equations. So in the universal, let's say take a final G variety with finite number of orbits, and we consider period in the sheave that we just discussed, which is important, as I said. And we assume the tautological system is complete. So you solve exactly the period integral. Then we are interested in subvarieties on B, which are invariant under monodromy. And we fix a differential, we do it by looking at the following thing. We fix the differential operators in dV's hat, which is homogeneous under the group GM acting on V hat. We want to describe the shield set cut by the local system, which we call del pi omega. So what are they? These are exactly the right-hand side here, the element in the parameter space, so that differential operator acting on the period integral is equal to 0 at that point. So this is a function defined on the parameter space. It should be vanishing there. So we are looking at the vanishing points, shield sets cut out by the local system. So this is a question actually of study by many people. It's a shield set of classical hypergeometric functions, and it begins by study by many people. And so we consider we projectivize this n delta and look at its closure in the projectivize V hat. Well, this turns out to be an interesting thing to do. And take a operator del, which is homogeneous under this action. Then it turns out the closure is actually is an interesting variety in which we can compute sometimes. So we conjecture that if delta is homogeneous under GM with order at least 1, then the shield set is non-vanishing. And this can be looked at in some special cases. So these are monodromy invariant subvarieties. And for example, take x equal to p1. In that case, things are a little bit trivial, but you can still give non-trivial answers. It turns out in that case, the projective closure is actually a curve of degree d. Now let me do a little bit more interesting statement. So basically, we can understand the question in the following way. I want to understand the shield locus of the vanishing of the differentiation. So B belongs to it. We want to characterize it. It turns out to be characterized by some algebraic formula. So I don't want to go into great detail. This G is the differential operator obtained by the G actions. And this R is a ring that we discussed earlier in the formula with Spencer Bloch and others. And so we can compute the B in terms of some linear algebra, actually, it turns out. So this can be proved to be true. And this gives us some interesting statements, which I just want to say a few words about. So this very, very special case is this is the elliptic integral, elliptic curve, and formula for the periods. And it's said like this. If I rewrite this change of variable to look at the omega, look at that in our formulation, then we use a B0 up to B9. You remember we have a different way to write the V hat. This BI comes in there. And J will be just this function. And the classical each elliptic curve would be just this cubic curve. And G2, G3 would be sitting in the parameter space A invariant under PGL3. And under the space change in this way, so it's a different change from BI to J. The phi J, the solution is actually can be written in this form. Okay, phi J is written in this form. So in terms of B variable now. Now the formula that I wrote down earlier can be computed. Maybe I skip most of the thing. And it tells you the following thing. If I take a del, a deformation operator, and it will differentiate this formula to be equal to 0 if and only if B satisfies these algebraic equations, which can be computed if I write down the coordinate carefully. So this gives rise to a way to calculate where the points who are zeros of the differential operators. Okay, now I want to skip to a different talk in a way with density we have discussed in the last 2 years. So these are two-dimensional ADE singularities generalized to more general situation. And so in this series problem, we understand the three-dimensional analog of 2D ADE singularity to use it to study superconformal field theory for d bigger than or equal to 4. The major thing we try to understand is to introduce differential geometry to understand this problem. So let me explain a little bit. So there's given a canonical singularity, which can be defined in the following way, given any specified is a Cartier divisor, if the Kx is Q Cartier, and also satisfy this property whenever you resolve the singularity, the canonical bundle satisfy this with AI bigger than or equal to 0. So that's called canonical singularity. If AI is strictly positive, it's called terminal singularity. So ADE singularity in 2 dimensions was classified, and it's here. And it was used by many people, of course. So there are some standard properties known to algebraic geometers. And so we have an index, the index R that we discussed earlier. When its index equal to 1, we call it rational Colonstan singularity. And there exists clip-on partial resolution so that this holds. And now, the index 1 terminal singularity is classified by the following isolated CDV singularities here, where F is the standard ADE singularity. So the complete classification of 3D canonical singularity are known in some cases, but we are most interested in this last case. So these are quasi-homogeneous hypersurface singularity satisfy this scaling law, where summation Qi is strictly bigger than 1. So it turns out this kind of singularity can be used to study several 4-dimensional n equal to 2 superconformal field theory, and even 5-dimensional n equal to 1 superconformal field theory. So we are focusing on the constraint on X from superconformal invariance and the description of quantum moduli space here. So this is the basic first of about n equal to 2 superconformal field theory. 4D dimension, it has a SO24 cross SU2 cross U1 symmetry group. And so it has also the Coulomb branch, which satisfies all these properties. Now, we learned from this paper, Shapley and Waffer, and so 4D n equal to 2 superconformal field theory, we can put down type 2B string theory on the following background, where X is a free-form isolated canonical singularity with several constraints. Namely, X admits a C star action, so it's a U1 symmetry, U1R symmetry. And there's a mini-versal deformation of the singularity, set like this. And so there's also a Cordillera Spencer map characterizing infinitesimal deformation, and we can read the Coulomb branch spectrum from it. So, the mini-versal deformation for hypersurface singularity has this type, where F is original hypersurface, and you deform it by using this Jacobian algebra. So these are the gradient of the F. Well, it has several. When you go to 5D, and you have, let's skip 5D. Now, there are chiral operators which form a chiral ring. And U1 symmetry group acts on these operators. The moduli space can be read from the chiral ring. So type 2B string theory on the following background is interesting for us. So we get D3 planes on the tip of X. We need to impose several conditions on X. First of all, there's an effective C star action on X. And then the major thing we study here is that we introduce a concept of K-stable on the chiral ring here. So the K-stability is interpreted as the stability of the chiral ring of field theory. So we define the stability making use of the analog with the geometry that we encounter in understand X, which provide an interesting geometric motivation for study stability of the chiral ring. So, so it was argued that the superconformal field theory is due to type 2B string theory on the background, where K is defined as a 5-dimensional ring of X, and K admits a Sasaki-Einstein metric. So the ring, the cone over this is K is a nice, interesting thing, because the cone over K is actually Calabi-Yau. And in this case, the stability of the chiral ring appear in superconformal field theory is equivalent to the existence of Sasaki-Einstein metric on this ring. So, or equivalent to the existence of rigid flat cone-like metric defined here. So that's our motivation. So the existence of the Sasaki-Einstein metric or the rigid flat metric on this total space is the stability question. So in fact, existence of rigid flat cone-like metric was conjectured by me a long time ago, 30-some years ago, to be equivalent to stability. And so Donaldson make it more precisely and introducing the notion of K-stability. And so we can just say a few words about it. So given a polarized ring, which has a U1 light symmetry, then K-stability has several ingredients. Some of them were fundamentally studied by these two authors. So Tristan Collins has been working with me in the last few years, so I learned from him about all this development. So first of all, you take a test configuration. It's similar to proof stability for vector bundles. When you use a one-parameter family eta acting on X on this space, then you take a flat limit to get a new ring, X0. So this will be a candidate chiral ring of a superconformal field theory. We define a Futaki invariant associate this whole thing, and we say X0 is stable, is not stable, if F is less than or equal to 0 for X0 equal to X0. This needs a little bit more explanation, but roughly speaking, we copy the whole thing from the situation in geometry, differential geometry. So the test configuration has one more symmetry group generated by eta. The Futaki invariant turns out can be defined in the following way. We calculate the Hilbert series of X with respect to this symmetry group, zeta. So H alpha, dimension H alpha T to the power alpha, is a subspace of a phi ring of X. So X is a singularity, has a singularity. You can define a phi ring for it. And so it has charge alpha under the symmetry zeta. So this defines a power series, and A0 zeta is inverse proportional to the tri-central charge A. So you write T to be exponential minus S, so S is log minus log T. And this A0 zeta turns out to be inverse proportional to the central charge. And turns out this was studied also by, about 12 years ago by James Park and Martinet. James Park was my postdoc at that time. So the true U1 symmetry and the central charge can be compute by minimizing A0. There we maximize the central charge. So here you're minimizing A0. So one can similarly consider Hilbert series for X0 with respect to the extra one-parameter family of symmetries, and we can define the A0. So we have a similar Futaki invariant defined this way. And then this turns out this simple-looking Futaki invariant, although it looks different, but it's the same as the one defined by Donaldson in the case of geometric situation. So that turns out to be very compatible in every way. So that's pretty good. The Futaki invariant actually turns out, we look at it carefully, it turns out to have these pictures. So this destabilizing configuration gives less A0 and therefore more central charges. So K-stable is then interpreted as generalized, the A maximization. We studied that with James Park and Martinelli. And this gives rise, this new ingredient is that one has to consider family chiral rings to do a maximization. So this gives rise to some geometric understanding of the superconformal field field that comes up. Now there are more detailed explanation to all this, but let me not do that. Just stop here. Okay. Thank you.